So in this lecture, we're going to be talking about some really beautiful mathematics, some of the most elegant mathematics that describes the beauty of geometry. And in that, we'll not only see these extremely elegant proofs of theorems that were known to the ancient Greeks, but we'll also be giving examples of some methods of inquiry and methods of discovery that I think can be applied in all sorts of arenas of life, even not mathematical ones. One particular one is that we'll look for the essence of things. Why is something true? What is the essential feature that makes a property true? And we'll see some examples of that in this coming lecture. And the second method of investigating the world is to take a complicated situation and decide, no, that's too complicated to work on. Instead, I will first investigate a simple reflection of it, a simple case, a simpler example that's not quite the whole picture, but we'll train ourselves, we'll pick ourselves up by our bootstraps so that we learn enough that we can then apply it to the more complicated situation. Well, the great thing about what we're going to do today is to start with a theorem that has one of the longest histories of all theorems in mathematics. And in fact, if you were to choose one theorem to represent all of mathematics, I think you'd probably choose the Pythagorean theorem. The Pythagorean theorem says that if you have a right triangle, such as this one, that the square on the hypotenuse is equal to the sum of the squares on the other two sides. Most of you have heard of the Pythagorean theorem. Probably everybody's heard of the Pythagorean theorem. But I bet most of you don't know how to actually prove that that's true. Well, one of the things about the Pythagorean theorem that makes it so attractive to me is that it shows that mathematics is timeless and completely universal and global. People have been thinking about the relationship of the Pythagorean theorem from at least 1600 BC to the present time. So it just easily shatters the bounds of time. So that's a wonderful feature of mathematics, and particularly this particular theorem. And we saw actually in one of the lectures, lecture number 3, we saw that the Babylonians had given examples of right triangles where that had whole number sides, like a 5, 4, 3 triangle. So that was an example from ancient Babylonian times, and they occurred on clay tablets, remember, 1600 BCE. But Pythagorean theorem is named after Pythagoras, and Pythagoras started a society in ancient Greece in 540 BC. And it was an interesting society. I wanted to say a couple of things about the Pythagorean society. It had a very strict code of conduct. And one of the features of it was secrecy. They would discover these mathematical insights and then not tell anybody. It was a secret. And I fear that concept of keeping mathematics secret from the population has endured to this day. I sometimes fear that we mathematicians don't actually divulge the inner essence of the mathematics, but I'm hoping to break that pattern today. So Pythagoras, the Pythagorean society actually had 3 tenets at least. One of them was the secrecy that I said. The other is that they were vegetarians, no meat. And the third one was a curious one that said they were not allowed to eat beans. Now, I'd be happy to go along with this because I don't like beans, so I think I'll join their society in that particular aspect. Well, so Pythagoras knew a proof of this theorem back in 500 BC, but the question is, the proof I'm going to show you right now was actually invented in India by a mathematician named Bhaskara in the 12th century AD. So this is showing the global universality of this concept. Well, Bhaskara is a wonderful mathematician, and I wanted to tell you one story about him before I give his beautiful proof. The story goes that he had a daughter who was going to be married. And the daughter, since he was a mathematician, back in those days there was a lot of overlap in the subjects, he was also an astrologer. So he had predicted the perfect time for his daughter to be married. Well, they had a water clock that was measuring the time, and his daughter had leaned over the water clock, and a pearl from her necklace fell into the water clock and blocked the water from going out. And because it blocked the water, the time was stopped, and they missed the propitious moment for her wedding. So Bhaskara did not allow his daughter to be married, and so I don't know whether she was happy about that or not, but in any case, she wasn't married, but he did write a book of mathematics that bears her name, and so she has lived through history by this tribute to her lack of marital status. Okay, well anyway, this is a story of Bhaskara, but I will now show you his wonderful proof of the Pythagorean theorem. So the Pythagorean theorem says that the square on the hypotenuse is equal to the sum of the squares of the other two sides. So Bhaskara said, well, if you're going to talk about the square on the hypotenuse, let's make a square out of whose sides are the hypotenuse. In order to do that, we need 4 different copies, identical copies of our right triangle. So we have 4 copies here, 1, 2, 3, 4, and he arranged them so that it was a square. So here we go. We just arranged them so that the hypotenuses are all facing outward. Here they are. See, this hypotenuse has got to face outward. You arrange them into a square like this. Fits very neatly, 4 of them, and then you need a little square in the middle to fill it out. So this is a square on the hypotenuse. Now look what happens if I just rotate 2 of these triangles. Rotate this one, rotate this one. And now the same amount of area has constructed this figure. But look what happens. If we put this little marker right here, you can see that this is equal to a square on the shorter side of the right triangle plus a square on the longer side. So he geometrically showed that the square on the hypotenuse is the sum of the squares on the other two sides. That's an amazingly beautiful proof of the Pythagorean theorem. We didn't need to write down a single equation or any other thing to prove it. Let me show you another extremely elegant proof, and it uses the same 4 copies of the right triangle. Here's another proof. We just put arrange the 4 copies of the right triangle we're working with into a little square, and notice that if you arrange them in this fashion, that the inner part is the square on the hypotenuse. So in other words, the total area of this bigger square is the sum of the four copies of the right triangle plus the square on the hypotenuse. Let's just rearrange these. Once again, we'll just rearrange these triangles. Rearranging them in this fashion, we see that the missing area is now the square on the short side plus the square on the big side. So that's another proof of the Pythagorean theorem. Aren't these great? These are just wonderful proofs. But finally, I wanted to show you that the presidents of the United States actually had a contribution to the Pythagorean theorem. President Garfield has his own proof of the Pythagorean theorem, which I will now show you. This is President James Garfield. What he did is just use 2 copies of the right triangle and then completed, he completed this trapezoid. You see? There's a trapezoid. This side is the short side plus the long side. We could call them A plus B in height. This side is B. The top is A. And the equation of the area of a trapezoid is the height, A plus B, times the average of the base and the top. So it's A plus B over 2. So it's A plus B times A plus B over 2. If you, that would give the area of the entire trapezoid. But this trapezoid is equal to the area of this piece, which is A times B over 2. Base times height over 2 is the area of a triangle, plus the area of this piece, A times B over 2, plus the area of this piece. Well, look, this is a right triangle whose height is the c, the hypotenuse. So the area of this triangle here is the hypotenuse, c times c over 2. If you just write the equation that the area of the trapezoid is a plus b over 2 times a plus b, and you set that equal to the sum of these three areas, and just do a little algebra, which you'll see on the screen, you'll see that you conclude that c squared is equal to a squared plus b squared. So that's James Garfield's proof of the Pythagorean theorem. Well, so this is, I think all of those are wonderfully elegant demonstrations of the truth of that relationship between the sides of a right triangle.